Hi folks. Because you're honor students, you need to know how to do gas stoichiometry even if we're not at standard temperature and pressure. So we're just going to have a quick look at how to handle those kinds of problems. What volume of carbon dioxide forms from the decomposition of 1.26 moles of calcium carbonate at 2 atmospheres of pressure and 0 degrees Celsius? Calcium oxide is also formed. So this is quite similar to an STP gas stoichiometry problem that we did previously. The balanced equation here is just calcium carbonate decomposes to form calcium oxide and carbon dioxide. So it's a 1-to-1-to-1 mole ratio. The basic idea with doing gas stoichiometry that is not at standard temperature and pressure is that you do stoichiometry as much as possible, but instead of using that 22.41 or 22.4 liters is the same as 1 mole, instead of using that conversion, you stop the kind of dimensional analysis stoichiometry part and you use the ideal gas law instead. So if you are given if your known is in liters, then you have to use the ideal gas law first and then do stoich. If your unknown is in liters, then you do the stoich first and then use the ideal gas law. So we're talking about doing stoichiometry and using the ideal gas law, which is PV equals nRT. So in this example, what volume of carbon dioxide, our unknown, is going to be in liters from the decomposition of 1.26 moles of calcium carbonate. So I'm going to just start with regular stoichiometry. I've got 1.26 moles of calcium carbonate, and I'm going to get rid of 1 mole of calcium carbonate for every 1 mole of carbon dioxide that I bring in, because it's a 1-to-1 mole ratio. And because I ultimately want to convert to liters, I stop here at moles. Because once I have the number of moles, that's going to become the N value in my PV equals nRT equation. So I go ahead and solve for the number of moles here, and I just have 1.26 moles of carbon dioxide. And now I plug this value into PV equals nRT. My pressure is 2 atmospheres. So I have 2.00 atm. My volume is what I am trying to calculate. My N value is what I just calculated from my stoichiometry, 1.26 moles. My R value needs to be appropriate for a question that uses atmospheres as the units for my pressure. So I use the R value of 0.08206 atmospheres, liters per mole Kelvin. And my temperature in Kelvin is 273 Kelvin. Solving now for volume and reporting my answer to 3 significant figures. Solving for V, I get V equals 14.1 liters of carbon dioxide. So we're not learning any new steps to do this. We are just combining what we've learned in the previous 2 classes using stoichiometry and using the ideal gas law. Let's do another example where we start with a volume of gas. So we're starting with 52 liters of oxygen. This time our known is in liters, and we ultimately want to calculate the mass of iron 3 oxide formed. So if we start with 52 liters of oxygen, but we're not at standard temperature and pressure, I have to use the ideal gas law first to calculate the number of moles that I can then use in a stoichiometry problem. So if I do PV equals nRT, this time I'm solving for N. I know my pressure is 98.0 kilopascals. I know my volume is 52 liters. I don't know my N value. I have to choose R that's appropriate for kilopascals. So I'm going to use my 8.3145 kilopascals per liter over moles Kelvin. And my temperature value is 265 K. If I solve for N, rearrange and solve for N, I get an N equals 2.3128 moles. Now, this number is only accurate to 2 sig figs, so I should round off here, but just to kind of avoid rounding errors, I'm going to leave the full value for dimensional analysis, and then I'll round off to 2 sig figs at the very end. So I'll start with my 2.3128 is the number of moles of oxygen that I have. And I'm sorry, we've done the same balanced equation in a previous example, and so I failed to balance it for you here. The balanced equation is 4Fe plus 3O2 makes 2 iron 3 oxides. So as you can see, we have for every 3 moles of oxygen we use, we produce 2 moles of Fe2O3. And I need to convert, because my final answer should be a mass in grams, I need to convert from moles of iron 3 oxide to grams of iron 3 oxide. And the molar mass is 159.70. So when we do the dimensional analysis, the calculator gives me an answer of 246.24. But of course, I can only round this off to 2 sig figs because my initial value only had 2 sig figs. A final answer rounded to 2 sig figs of 250 grams of iron 3 oxide. I hope this helped.